Hello everybody, Mr. Chan here with Algebra 2. We're going to start a new section today, 10-1, Operations with Matrices. Please grab your note takers and turn to page 235, and let's get started. We have a little opener here. This screen shows the number of small, medium, large, and extra large limited edition silkscreen shirts on sale at an online boutique. I want to point out that on the actual screen, the left side are for the blue t-shirts, and on the right are the red t-shirts. Construct a table, letter A, to summarize the inventory that is on sale. I'm going to look at the data and then decide how to construct a table. We use something called a matrix. The matrix is represented by brackets. And in this case, I'm going to go ahead and use row 1 for blue t-shirts and row 2 to represent red t-shirts. The data is on the screen there, and I know it's represented vertically, but I'm going to decide to switch it up and put it into rows here. The blue t-shirt represented by small, medium, large, extra large are, of course, 23, 53, 21, and 32. And likewise for red, I'm going to put that data in the second row. Now, normally you don't have to label everything, but it's kind of nice to see it. First column is small, second column medium, and so on and so forth. And there it is. It's a table that I've constructed that represents things that are on sale. Let's take a look at the second question. At the end of the day, the boutique has sold this many of each t-shirt from the sale items. Red, blah, 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 and blue, blah, blah, blah. Make 2 new tables, one showing the merchandise sold and one showing the inventory that is left. Now the data given to us is the sold data, so let's do that. I'm still going to create a matrix that is a 2 by 4. Those are called the dimensions that I'll talk about in the next page here. But here we go. And I'm just going to write that data down from the paragraph. So there we go. Watch out for where you put the numbers. They give us the red data first versus the blue data second. That's something that can easily mess you up if you're not careful. Always double check your data. Now, what's left would be how much they had and then how much they sold. You would have to subtract it. So left equals to the inventory that we have above and we're going to subtract the sold numbers that we have next to it. And we're going to just do some quick mental math there. That shouldn't be too bad, I don't think. So I'll be doing 23 minus 2 in the first row, first column, and writing the numbers down like right here. Let's double check that. Yeah, minus 2, minus 8, minus 4, minus 0 from the first row in the for sale matrix up there. Great. Second row, here are the numbers. Perfect. Very good. Give you a moment to jot that down. What relationship in C did you use in creating the 2 tables in part B? I decided to make my life easier. And you don't have to do that. You could have stuck with, a table that goes in the other direction. Each row represented the red and blue t-shirts. As long as you pick a particular norm, you just stick with it. Each column represents the t-shirt sizes. And of course, what's left is based off of just subtracting the inventory with what's sold. Okay, very good. All right, habits of mind. Edwin summarized the information given in the problem in 2 rows and 4 columns. In part B, he summarized information about the number of shirts sold in a table that had 4 rows and 2 columns. Was this organizational strategy helpful? Explain. Well, he did swap it, and that's what we decided to go with. Swapping the rows and columns can be a little messy when you're trying to process data. So when you have situations like that, you just have to double check your data itself. Let's go and formally define what a matrix is. Let's move it to the next page. Here we go. All right, so what is a matrix? A matrix is a table of data values. Those values are also known as elements. And what they use are rows and columns. Now, typically we use bracket, of course. The rows go horizontally from left to right. And columns, of course, are referring to the data going vertically. Each number inside the row or column is called an element. Each element has an address. That element, A sub mn, that's called a subscript, represents the number of rows and columns, the position. It's like an address. This is, of course, the address itself. The dimension of the matrix is an m by n configuration. This is called the dimension. Let's take a look at number 1 here off to the right. In matrix C, notice the letter C is capitalized. Matrix names are capitalized. And this particular matrix, the entries are the numbers of students on a committee. Column 1 lists girls, column 2 lists boys, row 1 lists sophomores, row 2 lists juniors. So let's go ahead and throw in some letters here to kind of remind us of that. Columns are girls, second column is boys, first row are sophomores, and second row is juniors. So I'm just going to use initials to represent that. Find A12, A21, and A22. They're just asking for the numbers, the actual data value itself. A12, of course, is referring to, of course, row 1, column 2. So row 1, column 2, the value is 5. Literally meaning 5 sophomore boys. A lot of times you can manipulate data that's in a matrix with spreadsheets. Portions of your computer programs have these, of course. when it comes to the actual programming language. Oh, let's take a look at A21 next. Row 2, column 1. So that's right there. That's the value of 8. In that case, 8 junior girls. Very nice. And of course, A22 is referring to row 2, column 2. That would be 10 as a data value, literally mean 10 junior boys. Okay, not too bad so far. I wanted to fit in, because we have a little space here, some vocabulary that you might run across in this section and this chapter. Sometimes they refer to equal matrices. What does it mean to have equal matrices? It literally means they have the same dimension. You know, the number of rows and the number of columns equal to each other. And when you have equal matrices, you can manipulate numbers in those positions, whether they throw in some variables or equations or elements. Each element, write this down, corresponds to each other's address. In math, the word corresponds kind of reminds me of when you're in geometry and you're referring to like alternate interior angles or corresponding angles. Those kind of things is referring to the same position. In the book, there's a quick example involving equal matrices and how we can solve. This is the one in the book, example 1C, and this is what it looks like. Write this down. We have a 2 by 2 equaling to another 2 by 2 matrix. And the elements are 12, 0, 2x, 10 on the matrix on the left. And on the right, we have 12, y, 14, 10. So basically, they're asking for, hey, solve for x and y, or what are x and y? Okay. It's actually pretty easy. You just have to know what they're looking for. If you take a look at this, the letter X is right there in row 2, column 1. It is corresponding, because of equal matrices, to the other matrices element on the right here. So it's just another way of solving algebra in a matrix form. All you have to do is just set those equal to each other, and that's it. Pretty easy peasy. 2x equals 14. Do a little math there. Undo operations, of course. X equals 7. Very easy. And the letter Y is up here in row 1, column 2. It corresponds to the left side's matrix. Oh, that equals 0. How easy was that? So that's pretty much it. So I just want to throw that in. It wasn't represented here in the note taker. I want to take some time to talk about equal matrices. The next example talks about something called scalar multiplication. Interesting. Well, you're probably wondering, isn't multiplication just multiplication? Kinda. In the next section, 10-2, you'll learn something called matrix multiplication, which is very different from scalar. Scalar is a little easier. Let's talk about that really quick. Scalar multiplication. All right. This is where multiplication of each element is by a single real number called a scalar. It's multiplication of each element. It's like applying the distributive property. That's all you're doing. By a single real number. And that's called a scalar. So right here in example 2, we have in matrix C, the rows represent prices for shirts and khakis. The columns have the same meaning as in example 2 in the book. Let's not worry about that. If the sales tax rate is 6%, and that's the key here, use scalar multiplication to find the sales tax for each item. There are 6 items here. We need to apply the 6% to the 2 by 3 table. Notice there are 2 rows and 3 columns there. 6% can't be used directly. We've got to convert that to a decimal. And that would be 0.06. And literally, I want to find what the heck 0.06 times C is. So that literally means 0.06 times every element in matrix C. And that's how you write it like this. You just put the number in front of the matrix, and it's implied that you're going to apply the 0.06 to everything. That's all. And of course, you can use a calculator, and I'll save you the trouble. We are going to, apply the 0.06 to the 2 by 3 matrix here, and you'll get these values. Here they are: 4.5, 2.4, 1.5, 6, 3.6, and 1.8. It seems a little pedestrian what we're doing, but this is stuff that is done on computers all the time, how the memory is manipulated, whether it's numbers, formulas, money, whether you're calculating video game graphics. It's all stored in a matrix. All right. Take a look at the bottom here. Let the dimensions of matrix Z be 3 by 4. After multiplying this matrix by a scalar, what are the dimensions of the product matrix? Interesting. Nothing changes. The scalar is just a single number that multiplies the elements. So here in this case, their dimensions will not change. And because it's multiplied by a scalar. When we get to the next section, though, when we multiply a matrix with another matrix, things get a little weird. All right, let's move on to the next page. Okay, it pretty much is a straightforward procedure when it comes to adding and subtracting matrices. It's actually very easy. You want to make sure when it comes to that, you have the same dimensions. The dimensions of the matrices you want to add or subtract must be the same. Here are a couple examples. In example 3, consider matrices M and N. Great, they're both 2 by 2s. What are the matrices of M plus N and N plus M? They're definitely the same right now. And they happen to be a 2 by 2. And we're going to go ahead and add them together. Now, is addition, whether with one matrix and then the second one or in reverse, are they the same? The answer is yes, when you add them together. So a tradition is to draw blanks. We're going to do some addition of all these numbers. In this case, M's numbers are right here, and N's numbers are right here. And when I add them, it's like 4 little problems. That's all we're doing. We get this as our answer. And we get the same if you add them in reverse. Yeah, it's the same. It's the same. The second question, I kind of jumped the gun there. Sorry about that. Same for both. Adding is a commutative property of addition. It's the same. Write that down. Commutative property. You may remember that from your Algebra 1 days. Ooh, what happens if you try to subtract them in different order? Let's take a look and do that mentally in our head. Let's do m minus n first. It's a little tight on space, I apologize. But let's do some mental math here. Row 1, column 1, here we go. -3 minus 6 is -9. 5 minus 5 is 0. 2 minus -8 is 10, because 2 negatives become a positive. And 0 minus 0.2 is -0.2. Versus n minus m. Let's see what happens there. I'm just going to do some mental math here. In reverse, 6 minus -3 is +9. 5 minus 5 is still 0. -8 minus 0. And finally, 0.2 minus 0 is 0.2. Notice they're exact opposite if you compare the two there. In fact, I can quickly prove it to you. M minus n, how does it compare to n minus m? You can always factor out a -1 from the second one, and you'll get dun, 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 -n plus m. And if you just rearrange it inside the parentheses, that -1 shows that it's the opposite. That was a quick algebraic proof there. Okay. Well, that wasn't too bad, was it? Just a quick little connection there. So there is no relationship other than its opposite if you try to subtract them. Let's take a look at example 4. Consider the matrices below. We have a P, Q, and R. Notice that they're all different, not just numbers or elements, but the actual dimensions are different. Let's just note them just in case. Matrix P is I believe, a 2 by 3. Matrix Q is a 3 by 2. And matrix R is also a 3 by 2. Zoom in a little bit more so you can see a little better. Very good. Okay. So find R minus Q. Let's do that right now. R minus Q, they both have the same dimensions. That's allowed. We're going to have 3 by 2. And let's do some mental math here. Okay, you guys ready? R is over here. So I'll just tick it off here. 6 minus 2 is 4. And you can do this on a calculator or manually. 0.5 minus 2 is plus 2. Great. Second row, here we go. -3 minus 5. 0 minus -5 is 0 plus 5. And then the last row, here we go. -2 minus -7 is plus 7 is 5. And then finally we have -2 minus 7 is -9. Okay, that was it. What other matrix sums or differences can be calculated? I'm going to give you a moment to play with that. I'm just going to start listing the ones I have here on my list. Try this on your own. And maybe you didn't think of some of these right here. Okay. The second part to part 4 asks about something called the additive inverse. Sounds familiar, right? From like elementary school. Let me remind you what additive inverse is off to the side here. Additive means what kind of a number you would add to get 0. Dun, 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 dun. So any number you pick, let's just use a generic m. Add it to something will give you 0. In this case, we call that the opposite. It is the opposite. That's what it is. Just -1. And when you put them together, the additive inverse with its opposite, you'll get its, da, 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 this is called the zero matrix, where the whole matrix itself has zeros everywhere in each element. So in this case, let's do that. Let's just go through the list of PQR. Negative P, the additive inverse, is equal to just negative in front of everything. Changing all the signs, basically. That's it. Same goes for negative Q. Not too bad so far, huh? A whole thing about matrices. A whole chapter, you might be wondering. What? Is there that much stuff? The type of matrices that we cover in this course is really a small part of what can be with matrices. There's a whole class that I took in college, a junior level class that we spent a whole semester on, and there was a lot of stuff. The stuff we do in this class, maybe it's about 5 to 8% of what we did in college. All right. So those are the additive inverses, and if you were to add the additive inverse to the matrix, you'll get the zero matrix itself. What must be true about two matrices for their sum or difference to exist? They must have the same matrix dimensions that I mentioned earlier. Okay. Ooh, let's get into something that's more interesting. We're going to be applying translations and dilations. Translation from geometry, you may remember, is where you shift the figure around. Dilate is where you would do making something bigger or smaller, kind of like your eye pupils, right? So that's when you make it bigger or smaller. This is where you stretch or shrink a particular figure. This is where you're multiplying with a big or a small number there, okay? So this is kind of interesting. You can take coordinate points and throw them into a matrix. So what I'm going to do is something that's traditional. We have a couple of points here, M at 8, -7. Those are your XY coordinate points. And we're going to translate them. Now, let me read further a little bit. I'm jumping ahead a little bit. A segment, as you know from geometry, is a straight line with two endpoints, and they are at MN in this case. MN is the, you might recall from geometry, it's called the pre-image. This is where you're coming from. And we need to translate it or shift it into a new name called the image, RS. And they tell us how we're going to shift it. We're going to shift it 6 units left and 3 units down. I mean, setting up the problem is actually going to take more time than actually doing the math itself. It's actually very easy and very fast. To represent a coordinate pair in this case, we're going to put point M and point N into a 2x1 matrix. And that 2x1 is representing an X and a Y. That's it. And what are we going to do? We're now going to combine this together and make it into a segment. So the segment itself are the endpoints of MN. It's almost like we're inventing something. And here we go. I'm just going to put the two matrices together into a 2x2 matrix like this. Bam. This is segment MN. And now we need to translate. Now remember, the first row are the x's. Remember that. And the second row are the y's. Remember that, okay? What are we doing with it? We need to translate, meaning we need to add a translation matrix. And watch this. This is going to be interesting. Remember, we are shifting it left 6, which means the x values are -6. And 3 units down, those are the y values. And we're going to go down -3, okay? So to represent that, in the matrix itself, left 6 is in the x's. I'm just going to represent by, it's kind of like a command that you might see in some computer code or something like that. Boom. First row, -6, -6. Second row, boom, -3, -3. That's all we're doing. And then when you combine that together, you get your final segment RS, represented by this, right? 8 plus -6 in the first row, first column is 2, 1 plus -6, so -7 minus 3, and 2 plus -3. Bam, there's your final segment RS. Okay, that's it. It's just doing something you've done before in geometry, but in a matrix. And it's kind of cool because it's kind of like a programming command. Letter B, we're going to try dilating. Dilating is basically multiplying by, in this case, let's see, use matrices to represent a dilation of mn to dE, okay, by a scale factor of 3. Oh, we're just multiplying by 3. That's all we're doing. We're multiplying by 3. Centered at the origin. What are the coordinates of DE? So let's just represent that. We're going to take matrix segment MN again. In this case, 8, 1, -7, 2. And we're basically throwing in a scalar multiplier like that. It's pretty easy. And here we go. 3 times 8, 3 times 1, 3 times -7, and 3 times 2. Hey. And that, ladies and gentlemen, is just another a new segment. It just happens to be bigger, segment D. And that's, of course, our scalar multiplier. Yay. All right, habits of mind at the bottom. They give us a 2 by 3. Okay, fine. Represents a triangle. There are 3 points here. First point, second point, third point. Use matrices to determine whether dilating by a factor of 2 and then translating 5 right is the same as translating the triangle 5 right and then dilating is the same. Does order of operations, in this case transformations, matter? I'm going to guess yes. You might say no. I don't know. Let's just see what happens if I multiply and then translate. Is that going to be the same as translating and then multiplying? Let's do it. So we'll do it in the first directive multiplied by 2. And then we're going to go ahead and add the 5 units right. Right are just the x values. That is just simply 5, 5, 5. We're not doing anything with the y value, so it's a 0, 0, 0 row. And what will we get? We'll get, let's do this, 2, 2, 8, 4, 6, 4. I'm just doing the math here manually. And this is my final. Here we go. 7, 7, 13 over 4, 6, 4. And is that the same as doing it the other way, where we translate the triangle first and then multiply by 2? And let's see what happens. I'm kind of using like parentheses and the 2 to represent. It's kind of like algebra almost, basically. Yeah. So what do we got there? 6, 6, 9, 2, 3, 2. And obviously, we are not going to get the same answer. So guess what? They are not equal to each other. Order of operations matters. All right. Let's jump to the last page here. Thanks for hanging in there. Doing great out there. Yay. Let's jump to number 5. Oh, identify the element. Oh my gosh. It's not too bad. I'm finished kind of fast. Let me know if you have any questions, of course. Ooh, identify the element for each matrix. We are looking for A at row 2, column 3. Ding, ding, there it is. That was pretty easy. No way. Oh, you're kidding me. How about this one over here? Row 1, column 1. Okay. Wow. Not too bad. How about number 7? We're adding 2 matrices together. Fine, fine, fine. Let's do that. We can almost do it in our heads. Try that at your desk mentally and look up when you're done. You might as well try number 8 as well. We're subtracting. Haha, good luck trying to do that in your head. We're doing B minus A. Be careful there. We're subtracting. Dun, 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 dun. Watch out for those double negatives, huh? Oh, there's more. Multiplication for number 9. Look up when you're done. Do mental math. Wow, we're multiplying everything by 4. Which happens to be the scalar multiplier, yeah. And you're welcome to write it out, of course. You don't have to do everything by mental math. You don't have to. Yay. So far, so good. And the final is A minus B. Ooh, it looks suspiciously this. Oh, yeah, look at number 10. Number 10 and number 8 are opposites. Because, you know, that's what we got earlier from that example. So can I just swap everything? That'd be pretty easy, wouldn't it? And I'm doing that because they're opposites. Yay. Oh, we only have one more to go. Yay. Number 11, the endpoints of AB are represented by this 2 by 2 matrix. Find the image of the segment after a dilation centered at the origin by a scale factor of 2. That's it. Kind of anticlimactic there. We're going to do 2 times the 2 by 2 matrix. Wow. Wow, wow, wow. Well, ladies and gentlemen, thanks for hanging in there. See you next time. Bye-bye.